Hello, welcome to this channel. This is Vale, and in today's video I want to explain the inner workings of RSA in a very short period of time. I originally wanted to do the full video with the full explanation, but I just spent 3 months trying to understand RSA as I am a newbie myself, so it would take a long time, plus I'm just simply tired. That is the reason I spent the last 5 days writing about it. I explained the whole thing in an article on medium.com, and I will be attaching that link in the description of this video. I would strongly recommend for every one of you who are watching this video right now to check that out. It has very long and vivid explanations, and everything about RSA that is I know is written there. So anyways, this video is mainly intended for people like me who has an absolute love for mathematics and science by itself, but never was good at it. For me, the reason being, as where I live, science is a very good subject, but just as a stepping stone to money-making success, but not just because it's an interesting subject by itself. So there are very few people who can, explain complex subjects with a visual ease and passion rather than throwing complex theorems and equations, which is of course very hard for people who are not mathematicians or never had an exposure to mathematics and science from childhood. So in my article on Medium, I started with the basics of number theory. Actually, it has very vivid and visual explanations on modular arithmetic. Then I slowly approached to group theory, which is only relevant to RSA because group theory itself is a very big topic. That's why I kept it just related to RSA. Then I showed RSA with a single prime number, which is very bad for RSA to be used in the real world, but it's great for understanding the specifics and understanding the inner workings of RSA. Then I approached the same thing but with two prime numbers, like the one that is used in the practical real world. So from that you can go explain yourself the workings of multi-prime RSA as well. So it's a long 1 hour read with 22 pages. I definitely recommend for the starters to read the whole thing slowly and calmly. It's more like RSA explained to a 5-year-old who only knows addition and multiplication. I kept it that simple and that clear that if you know multiplication and if you know addition, you can go ahead and get out of the chair with a pretty fair understanding of how RSA works. For the more audiovisual guys, this video shall give a fair overview of the framework of RSA, which can be cleared even more after reading the article that I wrote. So now getting started, I actually never thought I could understand RSA with its huge dependence on mathematics, but one day a YouTube video suggestion for RSA explained by Mr. Eddie Wu came in my suggestion, and he literally explained RSA in 5 simple steps. Now that explanation was so easy that it kickstarted me to go ahead and start researching RSA on my own. Now, I saw that due to lack of interest in the students and a lack of time, Eddie Wu wasn't able to explain the whole concepts and the whole mathematical explanations in a high level depth. So I'm almost going to repeat the same thing that Eddie Wu did, but with some clear explanations between some phenomenons because I am sitting at home and I have time. So that's way, at least people who know satisfactory level mathematics can understand the outline, and for the rest like me, the whole thing is written on the article. So I'm going to be talking about modular arithmetic on a very outline basis now, because whatever I want to explain or whatever I know about modular arithmetic has already been done on my article on medium.com. So I'm not going to waste much time and just show you modular arithmetic very formally. So remember this just for one time, that when we are talking about modular arithmetic, we are talking about a set of finite numbers. So when you look at a clock, you know that there is no number we can get past 12. So the clock has been keeping time from ages now, but we haven't went past 12. If we did, it would be probably a millionth o'clock, something like that. But still we haven't went past 12. So how did your brain come up with the way that you look at a clock? So if I say that it's 14 o'clock, what I actually mean is it's 2 o'clock. So how did your brain come up with the number that 14 o'clock means 2 o'clock? Now every one of those things are already explained on my article, so I'm just going to keep it very formal. So what does 14 means when we are talking about specific set of integers which has a limiter of 12. So I'm just going to type in mod 12. So what does 14 represent in mod 12? So what we like to formally call modular arithmetic is remainder arithmetic. So any number in the world, when performing modulo 12 with, what we actually do is divide any number. So maybe it's 76254, whatever. So 76254 represents what in a range of numbers with a limit of modulo 12. So just open up your calculator and write 76254 mod 12. It's going to be 6. So 76254 means 6 in modulo 12. So what I actually did was, if you divide 76254 by 12, you get the remainder, that is 6. So if you do the same with 14, so 12 times 1 is 12, the remainder is being 2. So 14 is congruent to 2 in a range of finite set that has a limiter of mod 12. So basically what I established right now is that modulo arithmetic is basically remainder arithmetic. If you want to find the congruence of every number that has a limiter of modulo 12, in this case, you just divide the number by 12 and the remainder is the same number that is congruent to the original number that you supplied. So for example, if you have selected 76254 and wanted to find out what it is congruent to mod 12, you just divide 76254 by 12 and the remainder is 6. So 76254 is congruent to 6 mod 12. Okay, let's directly dive into RSA now, and again it will be a lot outlined because the real explanations, the very detailed explanations, are all done on the article that I wrote. So I'll just keep on an outline basis. So I'll be taking the teaching approach of Mr. Rivest because that is very easy to explain. But in extra, what I'll do is explain some of the relations that you might get confused on how RSA works and how the numbers react in specific circumstances. So the way RSA works is, first it takes two prime numbers, alright? So let's say the first prime is 5 and the second prime is q, which is 7. So the product of the both of the prime numbers is 35, right? It can also be written as product of the prime numbers, that is n, equals p into q equals 35. It's the same thing, right? So what we want to do now is find all the numbers lesser than 35 that does not share any factors with 35. So one of them examples will be, for example, 15. Now 5 divides 15 and 5 divides 35. So 5 cannot be included in the list. So first let's make a list of the numbers that are coprime to 35, or in other words, does not share any factor with 35. So the numbers will be 1, 2, 3, 4, 5 will not be there because 5 directly divides 35. So 6, 8, 9, 10 will not be here, 11, 12, 13, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 31, 32, 33, and 34. Are there any numbers that I missed or included that is not a coprime? I don't think so. These are all the numbers that are lesser than 35 that are also coprime to 35. Now let's count the number of numbers that are coprime to 35. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, now one problem is the total number of numbers that should have been coprime with 35 is supposed to be 24. Why do I say that? Because without calculating all the numbers manually, you can also find out the number of coprime numbers only if you have the original prime numbers p and q. So what I wanted to say is, if you have the original numbers, that is p and q, then you can calculate the number of numbers that are coprime to the product of p and q, in this case which is n, without calculating or without finding out the GCD of each and every number ranging from 1 to the product of the two prime. So the way I can do that is, if we consider a prime number itself, for example 5, which is p in this case, so how many numbers are here that are coprime to 5? The interesting fact about prime numbers is every number except 0 in a set of prime numbers ranging from 0 to that particular number is a coprime to that prime number. So if you write 5 equals 1, 2, 3, 4, because we have already excluded 0 and we cannot write 5. All of the numbers in 5, and let's also write the same for 7, which is going to be 1, 2, 3, 4, 5, 6. Each of these numbers are coprime to their respective prime numbers. So 7 divided by 1, or so if we happen to perform a GCD of all the numbers ranging from 1 to 6 with 7, we will get a result of 1. If we perform a GCD of the numbers 1 to 4 with 5, we will also get the number 1. So we know from this fact that in case of every prime number except the 0 and the prime number itself, all of the numbers that is lesser than the prime number, they are all coprime with the prime number itself. So if we wanted to find out the number of coprime numbers in 5, the answer would be 5 minus 1, right? Because 0 is out of the question. So 5 minus 1 is 4. And you can see that 1, 2, 3, 4 are the total number of numbers that are coprime to 5 is 4. Then again, total coprimes to 7 is 7 minus 1, that is going to be 6. So when there are two prime numbers and the total of their coprime numbers is literally one number less than the number itself, then what Euler suggested is that if we have the multiplication of the original two primes, which is in this case 5 into 7 is equal to 35, the total number of coprime numbers in 35 will be the product of the total number of coprimes of each of the prime numbers itself. So what was the total coprime numbers in the prime number 5? It's 4. And the total number of coprimes in 7 was 6. So let's write 6. And the multiplication is 24. So the number of coprimes in 35 is now 24. So how RSA works is you can take any number within 35 that is coprime to 35. So we can take for example 13. If I just exponent it with 24 plus 1, I will still get 13 mod 35. So let's test this theory out if it actually works. So 13 to the power of 24 plus 1 is 25, so 25, I'm getting some ridiculous big number. Mod 35 is still 13, see? So RSA uses this property. If 13 was the message in this case, if the message was 13, then we know that there is a particular setting, that is 24 plus 1 will always recover the message 13 when performed mod 35. So what we needed to do is we have to generate two keys, the private key and the public key, that is basically representing this exponent 24 plus 1. Now the question I asked to myself when I was first taught this was, what is the relation between the multiplication of coprimes, that is 24, to the multiplication of the original primes, that is 35? Because it didn't make sense to me, because why this works actually, why exponentiating 24 plus 1 to 13 to mod 35 gives me 13 back. I had no idea, except this part was not explained in Edivo's video. This is what I am going to show you new. That is, take any numbers, maybe 4. Let's test with the number 4. The interesting fact about what I am trying to tell you now is there is something called the order of the element and order of the group according to group theory. Okay, so what I think about group theory, what group theory is, that is all explained in the article. I am just going to give you an overview. So take a number 4 that already belongs to the coprime list. So let's take 4. The interesting fact is that 4 to the power of 24, the 24 being the total number of coprimes, this is only the relation which I didn't understand at that time. So 4 to the power of 24 is always going to be congruent to 1 mod 35. Let's check this out. So 4 to the power of 24 mod 35 is always going to be 1. Now this phenomenon is called the order of an element that belongs to a group mod 35. So I'm talking about a multiplicative group, and what is a multiplicative group, what is an additive group, everything is explained in my article. So anyways, any of these numbers, they form a group, alright? All of the numbers that are coprime to 35, they form a group. In that group, any number you take, if you exponent with the order of the group. Okay, now one thing, what is the order of the group? The order of the group is basically the total number of elements in the group. So the interesting fact here is that there is also something called an order of an element. So the order of an element in the group is the number of times the element is multiplied by itself, performed modulo 35 with, which will give us the result of 1 mod 35. Alright, so that is what happened. Now 4 to the power of 24 is 1 mod 35, we know that, but there is something I want to tell you. Let's check. 4 to the power of 6 maybe mod 35. See, it's also 1. So I just tried it randomly. I didn't have any idea about 6 right here. So 4 to the power of 6 is also 1 mod 35. Then again 4 to the power of 24 is also equal to or congruent to 1 mod 35. Now the thing I want to say is the order of the element 4 is actually 6. Alright, because this 6 is the first or the least exponent that gives us the result 1 mod 35. But so it does when we exponent 24, then perform a modulo 35, which gives us 1. So what does this mean is, this is by part of Lagrange's theorem, that the order of the element, if there is one, then it always divides the order of the group. So what is the order of the group here? The total number of coprimes, that is 24. And what is the order of the element here? That is 6. So the order of the group was 24. The order of the element is 6. So 24 is divided by 6 evenly, right? 6 4s are 24. So if 4 raised to the power of 6 gives us 1 mod 35, any multiple of 6 will give us the same. So one of the multiples is also 24. So 4 to the power of 24 is giving us 1 mod 35 as well. Now, if you multiply any number with 1, it becomes that number, right? So if you multiply 7 to the 1, we get 7. So when the element was 4, if we do the same, that is 4 to the power of 6 into 4 mod 35, it is bound to give us 4. So 4 to the power of 6 into 4 mod 35 is going to be 4, because 4 to the power of 6, just like that, mod 35 is 1. So multiply another 4 with that, we get 4. So what if we wrote this in a simplified way? So 4 to the power of 6 plus 1, because by laws of indices, 4 to the power of 6 into 4, which means the 4 is the same base here, just the exponent is changing. So we can just also write 4 to the power of 6 plus 1. So 4 to the power of 6 plus 1 is going to be equivalent to 4 mod 35. So this 6 plus 1, 4 to the power of 6 plus 1, this is the one that we need to share. This is how we want to make two keys that we can share with Alice and Bob, for an example. That's how they can both ultimately do the same process that I am doing here. Now, one of the exceptions that I want to tell you here is that any element that doesn't belong to this range of numbers, so for example 15. Now, one of the thing is 15 to the power of 24 mod 35 will never come 1, because 15 doesn't have an order. If you calculate 1000 exponents maybe, it will never come to 1. And about this phenomenon, I have written another big paragraph on my article. But just know that it doesn't have an order doesn't mean when we are sharing this particular exponent, it will be equal to 15. So if we check on the calculator, 15 to the power of 24 mod 35 is giving us 15. It should have been 1, but it's giving us 15. But if we do the same, that is 15 to the power of 24 plus 1, which is 25, then perform mod 35 with, it's still giving us 15, and it will work for any numbers that are not in this list. So this is one little bit of exception that doesn't exactly follow the group theory, but I have written a lot about it on my Medium article. You can always check that out. So we have established that any number that is less than 35, which are not even in this list, by following or by sharing this particular setting, is going to be giving us the same number. So that's how RSA's algorithm actually works. So let's take a little bit of more time to explain the key generation process. Alright? Okay, so now let's talk about the key generation. So we have established that this particular setting, that 24 plus 1, if we exponent this number, that is 24 plus 1, to any of the numbers that is in this list or not even in the list, that is of course lesser than 35, will give out the same number when performed mod 35 with. So that's how as I already said, that is the phenomenon that we are going to use in RSA. But how can we share this number 24 plus 1? That is going to be the last concern. So I have to do something, maybe two keys. So key 1 combined with key 2 shall have to represent the number 24 plus 1. So how can we share this particular setting? That is, we want to share this setting. Share this setting. That is some multiple of order of element plus 1. We have to share this particular setting. So in case some multiple of order is also the order of the group, so we can also write the same thing as some multiple of the order of the group plus 1 is also the same thing. So we have to share this number. So if I write it mathematically, there is some multiple of order of group. So in this case it's going to be order of 35. Now this mark is called the order. Whatever I write within these two symbols, they represent the order. So order of 35, which is same as 24, which means some multiple of 24 plus 1 is maybe some number, So we have to make two keys that represent this sum number. So I can also say that M24 plus 1 equal to E and D combined, or maybe key 1 and key 2 combined, right? I can say that, right? So how can we do that? So now the original lesson or the first lesson comes back, that is modulo. We need to find two numbers that is basically similar to this number, all right, this particular setting. So in that case, key 1, I have already written it, right? Key 1 and key 2 combined is the same as some multiple of 24 plus 1. So we need to find two numbers that will be congruent to M24 plus 1. So we have some property called a multiplicative inverse in modular arithmetic. What it does is, we have some number A mod n, then we can have some number B which is the exact inverse of A, such that when multiplied, A and B completely reverts the changes or undoes the changes that is made by A mod n. Alright, so that's what we need in this particular case. So the way in RSA it works is, we have to find the A and B, or which is representing the key 1 and key 2. So A and B, we have to find A and B such that their multiplication, that is such that their multiplication, that is A into B, is going to be congruent to 1 mod the order of the group. Now this can be a little bit confusing, that why we need the order of the group here and why we need A into B 1. So multiplicative inverse is the same thing, because in a multiplicative inverse, such as say A into 1 by A multiplied by 1 by A is going to be the same thing as 1, right? You can also say this as 1 by A multiplied by 1 by A is going to be 1, right? But in modular arithmetic we do not have division but inverses. So in an inverted way, A into B is going to be congruent to 1 mod the order of 35. So we have to find an A and B that is equals, or that is congruent to 1 mod the order of 35. Then the way to do it is, there is a certain rule that if A and N are coprime, then there will exist a certain B that will be the exact inverse of A. So in this case the order of 35 is basically 24, right? So we have to find some number that is coprime to 24. So maybe 13 is coprime to 24. So let's say key 1 equals 13. So let's find an inverse such that 13 into key 2 is going to be congruent to 1 mod 24. So there is a way that you can do this, is called the extended Euclidean algorithm, but I'm not going to teach you that. You can just go ahead and look up in, on the internet. So you can just brute force here, maybe actually. So 13 into maybe 7, let's say 91 mod 24. is equal to 19, so that won't work. 13 into 5, 65 mod 24 is going to be 17, so that won't work. 13. Okay, so I'm going to exploit a property here, that is every number is also its own inverse. So 13 into 13 is 69, 169. So if I perform a 24 with, you see it's 1. So I am not, actually I am cheating a little bit here, because I am not supposed to have two same exact keys, because that would be very foolish in the real world, but for the sake of the ease of explanation I am doing that. So if the key 1 is 13 and key 2 is also 13, so 13 into 13 is going to be 1 mod 24. So that proves that 13 is its own inverse, and both of the keys, so key 1 equals to 13, key 2 equals 13. So in that case, if the 13s, if both of the 13s are combined together, it shall represent, so 13 into 13 mod 24 is the same thing as this, isn't it right? So if this as an exponent can recover a message mod 35, then so can this. Alright, so let's check it out. So let's take any number that is less than 35. Let's take 30. Alright, go on to the calculator, just say 30 into, now 13 into 13 is, it's 169, right? So 30, let's take the message as 30 to the power 169 mod 35 is still going to be 30. See, now let's check with another number, maybe 25 to the power of 169 mod 35 is still 25. So that's how RSA basically works in an outline. Now there are many much exceptions and many much more things to say, which I have already done on my article on Medium, so please go ahead and read that. But this is the basic outline of what RSA, or how RSA works like. I know it might sound a little bit confusing, but it is what it is, and if you study the article you will be very clear about how RSA works. So what happens in reality is one of these 13s or one of these keys is shared to the public, and one of these keys is kept to the server as per private key. So when you perform an exponent with 13, when you take a message, when the client takes a message, he performs exponent with 13, then he performs modulo with 35. He sends the encrypted message now to the server. What the server does is, it takes the cipher text, again exponents it to the inverse of 13, which is in this case 13, performs mod 35, and we get the original message. So in a nutshell, mathematically how that works is, cipher text is going to be, in this case only, 13 to the power of, sorry, maybe the message, maybe message is 25 to the 13 mod 35. So this would be the cipher text, where the plain text, how the server will recover the plain text is, plain text is equal to whatever the result is in this case. So cipher text again raised to the inverse of 13, in this case only, which is 13 mod 35. This means that the message is basically equal to message to the power of key 1 to the power of key 2 mod 35, or simply mathematically m equals to m to the power of encryption key into decryption key mod 35. So this is basically what RSA looks like. This is basically what this is how RSA actually works. But there is a lot of things I would have still wanted to say if this was a long video, but I didn't do that. That's why I wrote an article on Medium. So I suggest you go ahead and study it. Thank you. See you next time.